Hello and welcome back to Compiler Programming. With the executable and JIT code basically being able to execute simple programs, it's time to start working on a textual representation for our language, which means we need to start with turning strings of source code into some internal representation that we can do stuff with more effectively. Traditionally, you start with some kind of string, right? And then you turn this, you pass it through Tokenizer. So then it goes to Tokenizer or something. And that Tokenizer will return to you as a stream of tokens. So for example, this will be a token. Usually white space is skipped, but it's used to separate the tokens. Then you have another token, then you have another token. And the type of these tokens is also varying. So this will be like an identifier, this is also identifier, and this is a number. So this is the idea behind Tokenizer. And then in traditional compilers, you would then go into Parser that deals with this list of tokenizers and turns them into a tree. So we have like all operations group like that. With what I have in mind, I'm not sure we'll have a parser, but we definitely do want a tokenizer because dealing with strings directly is not very efficient and not very easy. So turning it into an easier to digest representation is a good idea. But unlike traditional tokenizers, ours will be a tree like it is in Rust. So instead of having it be a stream of tokens, what it will be is it will be a tree. And that just helps dealing with stuff like this a bit easier. So we do this parsing of the fact that this is a single thing already during tokenization. And this is the step that at the same time, I believe, simplifies some of the algorithms that we will use later on, but also helps maybe to not have parser at all and just jumping directly to more interesting things. But we'll see if we will end up needing it. For now, this is the idea. So let's start writing some tests. And it's always good to start with the basic options or basic edge conditions. So we should say that it should be able to parse or tokenize an empty string. Now, between the videos, I brought in my sort of base file that I use in projects, which is missing kind of standard library for C that I built for myself. And one of the things that it has this type they call slice, which is basically just a pointer to some bytes and the length of those bytes. I prefer this to using C strings because especially when you do some kind of tokenization or parsing, you usually want to avoid as much as possible to point to to create new strings. And if we were to create tokens that would if we would create a new string for each of the tokens of our source code, that would be extremely inefficient. And with C strings, we sort of have to do that, because if we say that, okay, this is a token and this is a token, but after each of it, there needs to be a 0 byte, that means that we can't just point to the same memory and say this is our token. So slice is the constructor that sort of allows us to do that. We just point here and say this is the length, but we are still pointing to the same region of memory, so we don't have to copy our source multiple times. And there are some handy functions that we can use later on to work with those slices. Okay, so we have slice source, slice from string literal, and we have an empty string, right? So now we can say token star token root or just root, because remember I told you it's a tree, it's not a list, so that means that we get a root node, and we say something like, well, tokenize of source, and we check that we get some root back, I guess, and well, the rest we have to figure out. We have to figure out what how to represent this type. So let's go to our source code and start thinking about what we want to do with the token type. So we say type def struct, and this will be our token. And let's see what we want to do. Since it's going to be a tree, we will likely need to refer to ourselves. So let's do that right away as well. And we need to figure out what is going to happen. I guess we will need also to have an enum, something like token type, that will tell us what is the token that we are looking at. So token type, we say token type, well, ID is definitely something to have, right? Then we would have an integer. I would make syntax such that white space is insignificant, so we will not produce tokens for it. It has certain disadvantages because if we would want to, for example, reconstruct the source code, source text from our token tree, we would need to, we would lose essentially the information about whitespace, and this is not good in general. So you, in a production environment, you would want to keep this information somehow, either through tokens or through other means. But for now, this is okay, and we can figure out how to do it later. Because the thing is, if you do keep this information around, it is complicating quite a bit the tokenizer and or parser. So for now, I'll just gonna ignore it. Okay, so we have ID, we have integer. We would have something like operator, so for plus, minus, and so on and so forth. And we also need to have, I guess we can call it a group. So something, for example, between these braces or these braces. And we also then probably want token group type or something to be able to distinguish between parentheses and other things. I guess something like that will be okay. So we say token group type paren, and then we have square brace, and we have curly, right? So those are the standard types of groups. We would also have a string, and this is a big question whether a string should be a group or not, and depends on how we deal with stuff like interpolation. So for example, in JavaScript, you can write a string that looks like foo, and then you do like this, and it would put a value of x inside of the string. So I haven't decided really what we're gonna do for string interpolation. There are various ways how to deal with it. So for now, I think I will go with just a plain string, like you see here in C. So no interpolation, and I might even want to not have escaping for now at least. So let's let's do the bare minimum that we can to make that happen. Okay, we need to change the values here. The reason I'm putting 1 here is because I want to reserve 0 as an invalid value. So if I debug something and I see a 0 in my struct, I realize, okay, I actually have forgotten to initialize it somewhere. So it's just a convenience for myself, how I'm used to debugging things. Okay, so we have token type, and we have a union. So what do we have? Another decision that needs to be made is at which point, for example, you would turn numbers into their actual representation. So let's say that we are parsing this file or tokenizing this file. And it doesn't matter that the syntax will be different, but tokens actually will be exactly the same. So it doesn't matter that this is C. Our tokenizer probably should be able to deal with this file. But the idea is when you come here, you need to decide what to do about this number. Do you keep the token as a string and just have it like, imagine in quotes 1, and then deal with it at a later stage, or you make it into an actual number? And this is not as easy a choice as it might seem, because it is probably best to keep it as a string and do conversion later, but you have to be careful to not convert it too many times because conversion from string to number is quite expensive. But the reason you would want to keep it as raw as possible, because you either will have to add support for something like arbitrary large integers, or you will have problems. Like if I have a number, something like this, right? And this does not fit into any integer type really, but before I realized that this is, in a later stage, I realized that this actually is going to be an integer. It is a perfectly valid number. And in fact, if I try to put this number into a float, it also is perfectly fine. In fact, in float, I can probably put it even bigger, and obviously it will lose precision, but it is still perfectly okay for me to put the float number in there. And C sort of sidesteps this problem by requiring you to do qualifiers and all kinds of stuff, but this is not very nice. So I think we will keep our numbers as just text right now. So that means that each token has a type and it has a slice, which we will call, I guess, source. Okay. If that is the case, then for regular tokens, this is all the read state, right? We will not really have anything more fancy than that. But for groups, we want more, because for groups, we actually need to have an array of stuff. So we can say array token pointer or something. Yeah, something like that. And this is going to be children. And now we need to define this type. So let's say type def dynamic array type of struct token star array token pointer. Okay. We need to also forward declare struct token, and this would be good. Undefined, yeah, okay, this is good. now we are ready to start working on our tokenization function. So we already know that it will return to us a token, and we will need to do something with the slice that we passed to it, right? So we have a slice source, and we need to do something here. So let's just say allocator, or we can probably use temp allocate as well. It's probably defined in value, so we can do temp allocate token. Okay, so that should make the test pass, as long as we also bring something in from our other tests, which actually sets up our stuff for temporary allocation. So let me grab quickly this thing and put it here. We want the buffer, and we want to clear that buffer afterwards. Okay, that builds. Let's see if the tests are passing. They are. So that's good. Now it's time to get a bit more fancy. So at the top level, we would expect it to be also special type of group, which is like a program. I could also just make it return an array of token, but since we have this logic to deal with list of tokens here, I think it's easier if we just introduce a special group type that will encompass the whole source code. Although program is probably the wrong one, it's more like module or something, because eventually we would have multiple files composing our program, and it would be nice if we can deal with these files. So let's do that check. We do check that root type is token type. Now that I'm looking at this, maybe I will just fold these into here. Yeah, I think this would be better. Yeah, let's keep it this way. It's just probably easier to deal with. Let's see. So we say that the token type is module, and now our test will obviously fail. So we can start doing stuff with it. Oh, I actually have not added this test to the list, which is something I should do, definitely. So we have source spec. It's fine. Let's try to run this. Okay. So our source has failed. The root type is not a module. Great. Let's fix that. So we say token star token is this. So we can say root is this. We say root type is token type module, and return root. Good. That makes it pass, and we can continue. What is the next test? Well, we could try to be very careful going step by step, but I want to have something more interesting right away. So let's tokenize an expression that is gonna be gonna have parentheses. So we just say 1 plus 2, something like this. Or for now, we can actually remove the parentheses. This is not a valid program, but from tokenization perspective, it should be a perfectly valid token tree, because what makes it doesn't make it a valid program is something that will come later, that will take this tree, interpret it, and kind of do some checking. For now, though, this should be okay. So we again tokenize the stuff. We can here we can also actually add another check. So we should check that array length of root children is 0. Now this thing is probably gonna crash because we haven't actually initialized the array for children. But let's see that. Yeah, as I thought, it does crash. So let's do that. So we say root children is array token pointer, and we say whatever, we'll have 32 children. Obviously, the top level will have much more than that, but that's fine. Okay, cool. We are back to passing stuff, and now we can start thinking. So what do we expect to happen here? Well, we expect to have 3 tokens in our list. Okay, let's add that assertion and figure out how we're gonna do it. And we can also say that we expect that the first element of this thing, let me probably say token star a number. A num is this. So the reason I'm putting this star here is because this macro, it actually returns a pointer to the item or the array, but because we are storing pointers in the array, we need to dereference it once, and then we will have our values. Okay. And the reason it returns pointers to the items array because other methods can return null, and I want to have a unified behavior. Anyhow, check a num type is token type integer, right? The second one is also supposed to be integer, and this is supposed to be a plus. So let's actually do it like this. Maybe it will be a bit easier to read. So plus type is token type operator, and b is also integer. Okay, let's try to run the tests, see them spectacularly fail, and continue to move on. This should be able to tokenize sum of integers. Good. And we are good. Great. Let's figure out what that would entail. Now we actually need to do something with our string. And this is where the basics are coming into play. Basically, let's grab this string so we have it in our eyes when we try to do something about it. And we can think what is supposed to happen when we try to tokenize it. Well, we are going from left to right on this string, and we need to figure out where does the token start, where does it end, and what is the type of the token. So let's think about it. Generally, for tokenizers, if you want to look up computer science theory or something like this, they are often implemented as finite state machines, which means that you have a set of states and a set of transitions between those states, and you take actions, usually on transitions, to do some stuff. And this is roughly how I will implement this, but not maybe precisely the canonical version of state machine. But let's do that. So we say in a state start, or maybe we can stay default. Then we would have state integer, state white space, and state operator. And then what we do is as we said, we go just from left to right and start to take actions. But the actions that we take depend on the state we are in. So this would be the loop, and we say for S8 char is, well, actually we should do it like this. 64i is 0, I is less than source length plus I, right? So we should never go beyond the source, but we should do something with every element of it. So now we can say that S8 char is source I, and we are ready to start taking action depending on what we are seeing. But as I said, those actions also depend on what came before it, so which kind of state we are in right now. And this is maybe easier to understand if I put something like this here. So when we see the first number, we should realize that actually we are now looking at an integer, and transitioning to state saying we are looking at an integer. When we see the second one, we are already doing something with an integer. So at this point, we will take slightly different action, different from what we did in the first step. Then we receive a white space and we realize, okay, we are inside of a white space. And at this point, we also need to take some action. So the first switch, therefore, should be on the state of our tokenizer, not on the... so we say state. I guess I will move it out right away and add a type def, and maybe clean up slightly how I wrote it. Tokenizer state, default, integer, white space, and operator. And actually default and white space probably can be merged into one. So yeah, let's try to simplify it as much as we can. So that means that we start in a certain state and we say tokenizer state is tokenizer state default, right? So we start in this default state, and then depending on our current state, we need to do something. So switch on state, we say case this, and then this. So let's just prepare the scaffolding for this stuff and then do some stuff. break, break, and break. Good. So what happens when we are in default state? Well, we will get this character and we need to decide what to do. Well, so that means that we need to have another nested switch in here that will switch now on the character, but in reality it's not really a switch because we will need to deal with ranges, right? So we need to figure out if what we got is an integer. I have a handy support function that says got point is integer. There is also, I think, is digit. Yeah, I think there is a standard function is digit, so we can use that one. So we can say is digit of ch. We do some stuff. Else if is space of ch. So if something is a white space. And basically, since we're considering our default state to be the white space, if we are in white space and we see white space, we don't need to do anything. We should simply continue our loop, right? So that's the easy case. Can even fold it a bit so more fits on the screen for the video. Okay, then we do something with digit, and then we need to do something with is, I'd like to say it's called is alpha for identifiers, but we can figure out if that's the right name for this function. And else we can say, sorry mate, we are not able to tokenize, we don't know what was going on. Actually, we should have a thing called code point is, well, let's not make a function right now, let's just make a custom thing for our plus, right? Because it also can happen. Okay, but if none of that is true, then we definitely assert and say unable to tokenize input. And we'll get back to better errors later. For now, I just want to have something going. Okay, source bytes I. So that's good. Okay, this does compile, so I even remembered all the function names correctly, but this still doesn't do anything, so it's okay. Now, we need to figure out what's supposed to happen here. So we get to a digit. What do we do? Well, we need to have some thing called like token star current token or something like this. So when we come across something that we would want to store for ourselves, we should figure out, we should store it somewhere. So that's what we will do. And another thing that we will need is, because in here we actually have this slice source, which gives us some information about the token, so like its range in the input. We will also need to keep track of that. So we will need to know what is kind of the start location of the of this thing that we are looking at right now. Okay, but for now we have our digit and we say current. Yeah, so if we were in default state and we come digit, that means that we definitely need to do this. Current token is this stuff, so we again allocate it, and then we say star current token, and we need to put some stuff into it. Well, the type of it is going to be token type integer, right? And the rest for now we can probably ignore. Is alpha, we can also say assert not implemented, because in our test we don't have alpha. If it is plus, then we can also do that and say that it is an operator. But besides that, it should be fine. But this is only in default state. But now we also need to figure out what to do in other states. Okay, so if we are in other states, we need to do something else. So basically it will be roughly the same thing here. And we need to just take different actions. If we come across a space, what do we do? Well, if we were inside an integer, right? So we're going here. Oh, let's say we're here and we come across a space. This is the point in time where we can say, actually, this is the end of the integer. So we can, we know where the token just ended. So the integer ended. And we basically almost always expect it to be a white space. It's either white space or it is the end of the input. But if we have something like 2a, this is invalid code, right? So that means that here we only need to deal with white space, and otherwise we say that this is something is very invalid from what you told us. Well, except for obviously the digit option. Okay. So what do we do when it is a digit, and what do we do when it is a space? Well, when it is a space, we just need to add it to whatever is the current root. And this will change over time when we have like nested structures, but let's keep it simple for now. So we just deal with one level and say that the root of this is going to be dynamic array push of root children, and we put current token in there. Okay, I missed a semicolon. Now it builds, but it still doesn't do what we want. Okay, if it is a digit, right now we'll just say we do like we should basically, no, we really don't need to do anything. So nothing to do. Good. Now, if we come across an operator, then actually when we are in operator state, and here, besides pushing the current token, we also need to switch the state of our tokenizer. So we need to say state tokenizer state integer. And here we say tokenizer state default. And in here we say that it's tokenizer state operator. Okay, integer and operator. Operator is basically the same thing. So if we are if this space, then we push the token and return to default state. And it doesn't even have if. It will eventually, because we would have a compound operator. So if you want to parse something like, double colon or triple colon or whatever, we'll need to do stuff here. But for now, plus is the only thing we support anyway. So let's keep it simple. Okay, that's all good and well. But we have now the final thing, because if we were at the end of the... So if we went through all source code, we might have a current token. In fact, this is exactly what will happen, right? Because we only push the token when it comes to a white space. And right now it won't be in white space. It will be at the end of the input, so we'll miss one. But maybe we can try to run the tests and see where it will fail. Okay, yeah, it fails in here. And I suspect, if I haven't messed up something, if I change this now to 2, it will actually pass this stage, and then we need to comment this out because this will be out of bounds access and we don't want to do that. Yeah, see, now we have everything passing. So our problem here is that, as I mentioned, we do the push of the token when we encounter a space, but we also need end of file. And if we were using something like a C string, we could switch on like 0 byte and use it for the end of input, which is one way to deal with it. I will just add another check at the end that will say that if current token, then just push it. And I need to if it for the case of empty string, right? Because if we have an empty string, we will never go inside of this loop. That means that this will be always 0. And if I don't protect against this, then it's going to be bad. Maybe I should write it as a comment. Current token can be null in case of an empty input. Okay, let's try to run tests, and we are good. However, if we try to look deeper in our tokens, then we realize we have a problem. And in particular, we need to keep the ranges of our tokens correct. And another thing I want to do is try to have multiple integers before we proceed. Okay, that is fine. However, what I want to do now is add the following check. I want to say that a num source, not source, slice equal. So this is just a function that basically compares 2 slices, so 2 ranges in memory. Slice equal a name source with slice from string literal, and this would be 12. Right, so we would expect to keep track of this range of bytes and saying that our integer is here, our plus is here, and this second integer is here. And right now we are not doing that yet. Also, while we are at it, we should do this and say that root source is going to be the whole input. Okay, so let's check that. Let's run tests, see them fail, and continue. Yeah, so first is root is not does not have source, but this one is easy to fix because for root we literally just do root source is source, and that should take care of that. but we don't have the right thing for the 12. And that means that we need to somehow deal with it. Okay, how do we do that? Well, when we create a token, what we can also do is say source is the following. It's gonna be bytes is source bytes I, and the length is 1. And if I for a moment remove this and put it to here and here, we should actually be able to pass those tests, I believe. So let's say that here is going to be 2 and here is going to be plus. Maybe though I will need to copy this into other tokens. Yes, something like this. Okay, let's try to run the tests. And we are passing. So what I'm doing here, again, because I just have this slice of memory here, and I'm going index by index, I can just point to a particular index where we are at the moment. So I is offset, and for example, for plus, we will be at this offset. So we say that our slice is just 1 byte to here. Now, another thing that eventually needs to happen is supporting for UTF. And I'm planning to just do UTF-8. However, again, I don't want to do it right now because it will just make the whole thing more messy. It's not really complex or anything. It's just really the tokenizer becomes quite messy because you have to deal with the valid UTF input, invalid input, and so on and so forth. We'll do it eventually though. It's fine. Okay. So we have this test passing, but we still will not have the enum passing because it is multiple digits. Okay, and this is exactly this case. We do have something to do. We need to say that current token source length plus plus. Right? This is basically the only thing we need to say. Okay. Test. Everything is fine. Let's add it to the index and think what is the next thing that we would want to tackle. Well, I guess let's change this one to be an identifier. So we also take care of that, and we say ID, and we say foo here. We say ID, ID, and ID. Okay, we'll run tests, it will fail, and we'll fix it. Good. Okay, so we have this is alpha, and we need to add another state to our tokenizer. And it will be basically exactly the same as an integer, and eventually we might be able to abstract this away, but I don't want to abstract it away before really looking at the structure and realizing what is the right abstraction for this. So let's not do it. Yeah, not sure if there is alpha num or if there is alpha or is digit. Let's just be explicit. Is digit of ch. So because for identifiers, we can actually do this stuff, right? We can put number at the end and it is a perfectly valid identifier. So let's just test that right away. Okay, we push. That seems okay to me. The one thing that we do need to do is do this stuff. And this already looks like a good candidate for abstracting this away a bit. But that is also something that can wait. Okay, so we have a problem, and the reason we have a problem is because I didn't switch to correct state over here. Right now we have everything great, and just like this we now are able to deal with identifiers. The whole thing about state machines is that they are a bit verbose, but they are at the same time pretty straightforward to work with once you get into the rhythm of doing that. So that's kind of a good and the bad thing about them. And with something like macros, we could probably make this stuff better. Okay, so what is next? Next is probably the trickiest part of all of this, and it is about groups. In particular, we want to be able to parse or tokenize something like this. So we have our module will have only one child, and that child is a parenthesized group itself. So we need to say something like this. We say parent, parent type, token type, parent. And then we also need to check that that thing itself has one child. And we get the child. And we verify that that child is an identifier. So let's copy this one. Let's just say that it is 0. It is a child of parentheses. And it is an identifier. We also should grab this stuff and verify the span of the of this thing. So slice equal parent source, and it should be the same way. Now there is a question whether we want to actually only include the insides or outsides of span. I think I want to of the group, but I think I want to include outsides as well, so including the parentheses themselves. Okay, we can do this. It will explode because we don't know how to deal with this stuff. Now, this is where it becomes quite interesting. So right now, if you look over here, we always push children to the root. But this is no longer true if we have these nested expressions. So we need to figure out a way to deal with this kind of stuff. And there could be a couple of ways how we can approach this. We essentially need to have a stack of tokens. And we can have a very explicit stack, so just have an array. But what I'm thinking is we could also have like a parent pointer inside of the token. And when we push a token, we also like keep the pointer to its parent. And when we are done, we just undo that pointer. Let's try it this way. I'm not sure if it will work out correctly, but that seems at least somewhat interesting to me. Root obviously does not have a parent, so that's something that we can also add as an assertion, and we say root parent is 0. But everybody else should have a parent, and maybe we should be explicit here as well and just say parent is 0. Because you never know if allocator zeroed out memory or not. Okay, That sounds good. Now, the question is, what do we do with the parent? Well, I guess we also need to say that parent is root, right? We start with root as being the parent node, so we now can say that, maybe I'll put it here, parent is parent, and here as well, and here as well. I think I'm just about ready to shove it into a macro, but maybe just a bit more. Okay, so that's fine because we are only failing on this test, and this is where we would still expect to be failed because we still have no idea how to deal with open and close parentheses. So let's do just that. And I'm wondering if we want to duplicate this logic everywhere or if we want to do it on a higher level. I guess I will do it this way. Even though like this is where I'm not exactly doing the very strict state machine, but I think it's just going to be easier to deal with this here rather than in every place. Oh, maybe not. Let's start with this option. So if we come across an opening brace, and then we say it is a parent, we switch out we take the parent, but besides switching the state, we also not need to switch the parent. So we say that parent now is current token. Yep. And yes, parent is current token, and we are switching state, and the state is again default. So we are actually not doing anything with the state because we are already in the default state. So we are only switching the state. And if we find the closing one, then we need to like sort of roll back this parent stuff. And this is what I was saying, that I think this one should go outside because otherwise we will need to copy it in every option, and it's not great. So I will just simplify the job for myself and say it doesn't matter in which state we are. If we came across the closing parenthesis, then we need to essentially pop the stack of the parent. So we say parent is current token parent, and we also want to assert that we had a parent because we have a situation, for example, if we have something like this, right, we would come across this closing parenthesis, and we will try to say that, okay, we now need to have a parent, but we don't have one. Okay, so parent and continue. That seems reasonable. This opens it, the other one closes it. And here we need to change push to be parent children instead of children. And here it should be, well, here actually we now can add more assertions, right? First of all, we can say that parent is root. This means that we avoid situation that is opposite of this, where we have opening brace, but we don't have a closing brace, right? So we never actually finished. that group, which is a good assertion to have. If we know that parent is root, then we can push current token to be the child of root. That seems pretty good to me. Let's see what happens. And actually, here I also need to say that I need to update the source, right? Well, let's try to run tests, and it will tell us what's wrong. Parent is root. That is unfortunate. So something is not working like I would want it to work. Let's see again what we're doing. When we okay, well, the first thing that is wrong is we do need to right away push this into the, well, actually, no, we don't. We can do it here. So we can push parent, children, current token, parent, children, current token. So this just pushes the whole parenthesized group into whoever should own it. So that's good. And the second thing that we need to do is we need to say current token source length is we are basically taking the pointer to the to current location, and we will subtract a pointer where we started to track it, and this will give us the length of that span. Current token source bytes. This probably should be like this. Okay, that still will not fix the, well, apparently this crashes pretty spectacularly. So let's bring out the debugger and figure out what is going wrong. This is going to be called source spec, and we can start this stuff. Okay, so we are spectacularly exploding inside of the thing, and I know why. Okay, so this is good progress. And the reason we are exploding is because we are not creating children array for the parentheses, right? Okay. Let's create one. Maybe have a smaller one for parentheses expressions. Majority of them will not be that big. Okay, now we are back with a root is not parent. So let me open source C, and we can try to figure out what's going on. So I'll just make a breakpoint right over here. I will run this. I will run 1, 2, and this is now our test with a parenthesized expression. So we go here, we switch of state. Okay. So we find that it is a open parenthesis. We create a token, and we do that. And we switch out the parent. So parent now should have type parent. Okay, that is fine. Okay. We are not in the closing. We will find alpha. We will find a token ID. And yeah, okay. I actually do know what's going on. So this is where the state machines become a bit verbose. So here's what's going on. We are in state ID and we come across this thing, but because I brought it up, it ends up not being pushed correctly. So yeah. So here we are pushing the child. Actually, that is fine, but we should also push it here. So like so. Let's try that again. Okay, I guess I need to do that one more time. That's fine, fine. And maybe to simplify matters, I will change this to be just x. So we have less iterations through the loop because we know our IT parsing already works and we don't need to do stuff with it. Okay, this is where we create our group. We push this. So our parent right now is a module and it has one child. Yeah, length is 1. That's good. Change the parent, we break. Okay. We come across an X. We switch to the ID state. We continue. And now we are in closing parentheses. So current token parent children. Well, actually, this can be just parent children, I guess. This is not really required. So parent is no, okay. Parent is parentheses. That's good. And the parent this is no, this is correct. Yes. So the parent of it is a module. So we switch parents, and we continue. Why didn't it do the right thing though? Oh, because yeah, this is the honest mistake. This should be parent. So we are unrolling our loop. Okay, let's try that. Well, that's better. We are making progress. So our problem right now is that yeah, so this is fine. This is not really correct. How do I want to deal with this stuff? I guess let's do the copy pasting for now. And then we figure out how to deal with it later on. So we are in ID state and we come across parentheses. We also do the same as with space. And we do need to change the state. We need to do this stuff. Actually, this is this shouldn't be current token. This should be parent. Yeah. Then we undo parent. We assert parent, and we are good. Still doesn't do what we want it to do, which is very interesting. So what is the actual number there? I want to have source back in my debugger. I want to look at this stuff. Okay. Apparently it blows up before that. I know what the issue is. The issue is that here I actually shouldn't be pushing this, but rather I should be switching back the current token, because there is this thing, right, where we have a current token. Okay, so what I can do is I can say current token is 0. This also should do the trick. Okay, well, that is definitely progress. Now we have a problem that the source is incorrect. Okay, so parent source length is bytes minus parent source bytes. Okay, let's check what is that thing, how big we think it is. Sorry, F5 and F10 and F10. Okay, we have parent and we have source, and the length is as 2. That's not correct because it should be +1. That's, off by 1 error is indeed one of the biggest problems in computing. Okay, so this is good. I think I actually can extract this to be over here. The only place where this would not work is when we get to tokenizing strings, but I think I will leave this for the next video. For now, this looks pretty neat, and I want to just try out able to tokenize complex expressions. So let's just do some crazy stuff composed out of what we have to make sure that we have stuff working correctly. So we say 42 plus foo plus 1, 2, 3 plus whatever. So this should parse just fine. I will not do this kind of checks. Later on, we will probably do snapshot testing. So we will basically capture this stuff and then store it in a file or serialize somehow, and then check that our tokenization is still correct, or maybe have some kind of DSL to specify those. I'm not sure, but having to specify these very large checks is not very scalable for bigger things. But for now, it helped us quite a bit, so it is good to have. Okay, well, at least it sort of parses, it doesn't explode, and I'm okay with that. That will be it for today. I think we made good progress. Now we can parse more complicated things. Obviously, there is more to do with different types of parentheses, maybe introducing some macros, cleaning this up, but all of this will come in the next episode. For now, thank you very much for watching and hopefully see you next time.